A manufacturer is designing a rectangular garden that is to be enclosed with a fence. The company has a budget that allows for a maximum perimeter of 60 meters. So perimeter of a rectangle is 2 times length plus 2 times width. Has to have a maximum perimeter of 60 meters, so it's got to be less than or equal to 60. The garden must also meet the following real-life restrictions. The width of the garden cannot exceed 15 meters due to space limitations. So we'll call this the width, okay? It cannot exceed 15 meters, which means it's got to be 15 meters or less. All right. The length of the garden must be at least 5 meters to ensure adequate growth space. So length has got to be greater than or equal to 5. All right. Which of the following measurements for the width of the garden cannot be used due to real life restrictions? So what we'll do is we'll go through the list, we'll plug stuff in, and we'll see what happens. All right. So A is going to have me plugging in 10. And by the way, width, that's the key here. We're talking about width. So I'm going to plug in 10 for W. So 2L plus 2 times 10 has to be less than or equal to 60. Okay, and while doing this, we are trying to make sure that our length is greater than or equal to 5. So 2L plus 20 is less than or equal to 60. Quick math, I'm not going to show my work. Subtract 20, 2L is less than or equal to 40, right? Divide by 2, L is less than or equal to 20. So this gives us a box that follows the rules where I would have a width of 10, which is fine, and a length of 20, which is good. And so my perimeter would still be 60. All is well, no complaints here. You check out, you are not a problem. If I were to try 5, I would do the same process. 2L plus 2 times 5 has got to be less than 60. Okay, so 2L plus 10 has to be less than 60. 2L, subtract 10 from both sides, is going to give you 50, right? Divide by 2, the length is going to be less than or equal to 25. So that gives us a box of 25, 25, 5, and 5. It's less than 25, which is greater than 5. Everybody's happy, everybody's good, no problem, we can do it. 5 checks out. And then we get to C and realize, boy, oh boy, did we waste our time. Because it says here that this is the width. The width can't be bigger than 15. So why in the world could it be 20? Well, all right. So, again, the point of this was for me, I showed my work anyway in the off chance this problem wasn't as complicated as it was. In this case, it's not complicated at all. I mean, the answer is screaming at you right there. 15 is going to work, trust me, but 20 is already telling you, yeah, it can't work based on these restrictions right here. So that's optimization. With optimization problems, and this is the intro to optimization, you are looking at restrictions when building real-life objects, and 20 screams at you that, yeah, that's a restriction. So much easier than it had to be. I just like to complicate things. I'm like Avril Lavigne, and why do I have to go and make things so complicated? Remember that song? You probably don't. You were too young. Thanks for watching. Like and subscribe. Your company has given you the task of creating an open box with a square base to be used for packaging. So we draw a picture, and I don't know what I'm doing, so that's the best I can do. The specifications for the box include using a 432 centimeters squared of cardboard and a maximum width of 20 centimeters. Great. You have created a differentiated volume function and found that the only crucial value, or I guess critical point, occurs at x equals 12. Interesting. The values of v prime, the derivative of the volume function, are shown in the table below. Based on the data in the table, what width should be used to maximize the volume? Now, whenever you're looking for maximum and minimums, right, in this case, we're looking for a maximum, you're thinking of a relative or local maximum, or in this case, local minimum if I wanted to add to it. Now, that happens when you know you're going from increasing to decreasing or decreasing to increasing, which means that happens when your derivative goes from either positive, so we'll say v of prime, goes from positive to negative, or negative to positive. So the devil is going to tell you, select this one, 81's the maximum, but that's actually not what you're doing. You are building yourself a sign graph because you're given V prime. These guys give you critical points, not maximum volume. Maximum volume is used by finding or by plugging stuff into the volume formula, not the derivative formula. So this is a critical point right here because it's 0, and this is a critical point, which means it's 0. So if I put what I have, I can put an 8 here, and I can put a 18 there. Based on my derivative, you're a positive number, which means between 8 and 18, I'm increasing. Okay, you're a negative number after 18, which means after 18, you're decreasing, which means a maximum occurs right there at 18. So since my maximum value occurs at 18, the maximum number is going to occur, the maximum volume is going to occur when x equals 18. So again, I think most people would look at this problem and assume that the answer is 12 because 81 is bigger than all these numbers here. But since we're given v prime, that is not what we're doing. V prime gives us the location of the maximums and the minimums, and those locations exist when it equals 0. So kind of a tricky problem, but I had fun. A manufacturer wants to create an open box by cutting out X-sized squares from each corner of a rectangular piece of cardboard measuring 10 by 20 centimeters. So let's do our best to try to draw that picture right here. Okay, so we have a rectangle. You would be 20, you would be 10. I am cutting out X-sized shapes, X-size squares, right, out of each corner. So X, 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 X. Now, what that does is the brand new length of these guys are going to be whatever this length is, 10 minus 2x. This length is going to be 20 minus 2x. So common sense would tell us that, like, I couldn't say, well, let's cut out 7 sized x's. Well, that doesn't make sense because if you choose 7, then you would get 2 times 7 here, which is 14, and 10 minus 14 means you're going to have a length of rectangle that is -4. That doesn't make sense. So one of these will not work, and that's the problem. After cutting these squares, the sides of them are folded up to form the walls. Great. Which of the following values cannot be used due to real-life restrictions of the dimensions of the box? Well, let's say you weren't thinking and you decided, well, let's go and test all of them out. If I were to cut out X-sized shapes, that means the length or width, whatever you want to call it, would be 10 minus 2 times 2, which is 4. So that would give us a box, right? That would give us a box with a height or whatever of 4. Actually, the height would be X, so we would call U 4. Can I move the 4? Yeah, no problem, no problem, no problem, no problem, no problem. And what would U be? U would be 20 minus 2 times 2, which is 4, so U would be 16, 16, everything's fair. But then common sense takes over and says, well, wait a minute. Why don't I pick this 5? Because if I decide to cut out 5 shaped X's, then this is going to be 10 minus 2 times 10, which is 0. So that means I'm going to have a box with, boy, am I awful at drawing these. I'm going to have a box, I give up. I'm going to have a box with a length of 0. Well, that can't happen. That's not a box. It's invisible then. So we decide C has got to be our answer because C cannot work. Because if I plug in 5 for C, or 5 for X, I get 10 minus 10, which is nothing. So I don't have a box anymore. Stinks. So optimization, you're looking for things that can't possibly work, and that was one of them. Fun, fun.